Hello everyone, welcome to Unit 7 review, which covers like materials. Um, yeah, so this also includes elastic potential energy. It says the formula of like 1/2 ks squared, where k is a spring constant, right? Yeah, so subscribe and then we'll get on with it. So number one, the variation with applied force of extension of the spring is shown in the graph. When there's no force applied to the string, it has a length of 1.0 centimeters. What is the increase in the strain energy stored in the spring when its length is increased from 2 centimeters to 3 centimeters? So the length is increased from 2 centimeters to 3 centimeters. This means that the extension is 1.0 centimeters to 2 centimeters because our original length is 1 centimeter, right? So we're looking at this 1 and 2, and another idea that is relatively commonly expressed in AICE physics is that when you have a force and an extension or like displacement, the area under this is actually just work done, or joules basically. It's energy. So when they're asking for strain energy, we're essentially looking for the area on the graph here. And in this case, we have 2.0 newtons. I'm calculating the actual area using trapezoids, multiplied by 1.0 centimeter. We have to convert the centimeters to meters, which is the SI units. So it's going to be like 1 meter over 100 centimeters. And if you calculate this out, you should get 0.030 joules, which is B. Okay, number two, the Young modulus of a metal may be determined from the ratio stress over strain when the metal is stretched elastically. This can be done by making measurements when loads are added to a wire. Which measurements are needed to calculate the stress and strain of a wire in such experiment? So you kind of have to know what stress and strain are, like the formulas for they are. So stress is actually force over area, where this is the cross-sectional area, right? Additionally, strain is just the change in x over x, where x is like the length of wire in this case, I think, or of metal. Yep. So when we're looking for the force and the area, we have to know like the area of the thing as well as the force applied onto it. So let's look at the answer choices. So wire diameter. Well, with the wire's diameter, you can actually calculate its area, right? Because it's technically a circle. So when we look at these two choices, it's not necessarily true that we need those, because we don't need the length for stress. We only need the cross-sectional area. Additionally, another part of stress is the force, right? So the initial and final positions of the load. Well, we don't really need to measure the initial final positions of the load. We only need to know the mass added, right? It turns out this is the only answer. If you look at the second part, which is the strain, right? So this is put over here, and strain is the wire's original length, which turns out to be the denominator, and then the initial final position of the load. Well, you can calculate the change in x through this, which is the numerator, and it turns out strain can be calculated using these two values. State what is meant by work done. So work done is going to be force times displacement in a certain direction. Elastic potential energy. Elastic potential energy is energy stored in springs. Wait, not springs, but just like, oops. Materials when stretched and compressed. Okay, so I'm reading a thing, and they do say spring, but essentially, the idea is that the material satisfies Hooke's law, I'm pretty sure. And that would make it more precise. Okay, next problem. A block of mass 0.4 kg slides in a straight line with a constant speed of 0.3 meters per second along a horizontal surface as shown. The block hits the spring and decelerates. The speed of the block becomes 0 when the spring is compressed by 8.0 centimeters. Calculate the initial kinetic energy of the block. So this is actually from a previous unit. Good review. So kinetic energy is equal to 1/2 mv squared, which is going to be 1/2 0.4 0.3 squared. 0.4 times 0.3 squared over by 2, and our kinetic energy is equal to 0.018. The variation of compression X of the spring with the force F applied to the spring is shown. Use the answer in BI to determine the maximum force exerted on a spring by the block. Okay. So one thing that we did do before, like in the first problem, is that the area under this graph is essentially joules, right? And this can be further exemplified through the usage of the elastic potential energy. So like EP is equal to 1/2 KS squared. And oh yeah, before I forget, one line of reasoning that you should make is that since they tell you to calculate the initial kinetic energy as well as now calculate the elastic potential energy, you can like kind of connect the dots that, oh, this block, it's hitting the spring and it's converting all this kinetic energy into potential energy. So then it turns out that you can just substitute the part from before, 0.18, that's our kinetic energy, right? Multiply by 1 over KS squared. I should say that this is also like F max, right? Times S. It's just a colloquial definition. And then our S in this case is 8 centimeters, which is 0.8, 0.08. And do calculation, hooray. Which is going to be 0.45 newtons. Explain your working. Kinetic energy is converted into elastic potential. Calculate the maximum deceleration of the block. Well, okay, so we know the maximum force, right? So from Newton's second law, we know that force is equal to ma. So our force is 0.45. Our mass, if you remember, is given. They tell us that the mass of the block is 0.4 kilograms. So 0.4 times A, and then A turns out to be 1.1. Four, state and explain whether the block is in equilibrium before it hits the spring. So in this case, the block is in equilibrium because the sum of forces is equal to 0, and even though is completely unrelated to like what we're doing, you have to say it because it's part of the definition of equilibrium. The sum of the torque is also equal to 0. And then number 2, when its speed becomes 0, well, we kind of just calculated it, I think, right? So it turns out when we reach our force max and like our maximum extension, our block is not moving, right? Because our kinetic energy is all in potential energy. So no, not equilibrium, because the sum of the forces is not equal to 0. Object is actively decelerating. Okay. Okay. The energy E stored in a spring is given by E equals 1/2 kx squared, where k is the spring constant of the spring and x is its compression. The mass m of the block in B is now varied. The initial speed of the block remains constant, and the spring continues to obey Hooke's law. On figure 3.3, sketch the variation of the maximum compression x0 with the mass of m. So it turns out that the more mass, okay, so we know that as mass increases, our kinetic energy should also increase. And we know that this increases linearly because kinetic energy is equal to 1/2 mv squared, and m is a linear term in this case, so it's going to be linear. So let's start it this way. But then remember what springs do, right? So eventually springs cannot compress anymore. So it turns out that eventually they'll just reach the bottom like that. A metal wire is stretched to breaking point, and the force extension graph is plotted, which graph correctly labeled with the elastic region, the plastic region, and the area representing the work done to stretch the wire until it breaks. So what I said like before in like this question here, the area under the curve of the force extension graph is actually going to be work done. So A and C, can automatically be eliminated because, well, look at this. All this area here is still work done. So it just excludes a large amount of the work done. But yeah. So now we're left with like B and D. Those are more accurate because they show the actual work done by the entire process, right? So recall that elastic means that when you stretch it, it goes back to original, right? And in this case, this is usually linear, right? So it doesn't make sense that this curve, wonky curve, is going to be like up and down, right? It's just going to be this linear right here. So in this case, it's not going to be B, it's going to be D, which is shown here, right? All right, next problem. A ball X moves along a horizontal frictionless surface and collides with another ball Y as illustrated. Okay. Ball X has a mass of 0.3 kg and initial velocity v of x at an angle of 60 degrees to line AB. Ball Y has a mass of 0.2 kg and initial velocity of this, blah, 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 blah. The two balls continue moving together along a horizontal frictionless surface towards a spring. And they're asking for the maximum compression of the spring caused by the two balls. So for this problem, you're going to have to use the elastic potential energy formula, which is 1/2 ks squared, which is also known as like 1/2 f max x f max s. But in this case, we're just going to use this formula. This is just a definition that you should know. But yeah. So let's look at our diagram real quick. So we're looking for the maximum compression, right? So the maximum compression happens when balls transfer, or I was going to write convert, transfer all kinetic energy to potential energy stored in the spring, right? And that's why we use this elastic potential energy, because we're solving for this, right? Since we know that the kinetic energy is equal to the potential energy, we can say like 1/2 mv squared of the balls is equal to 1/2 the k constant s squared. And then we just plug in some values that we know. So 1/2 mv squared, the m is going to be 0.5, our velocity is going to be 2.4, is equal to 1/2 ks squared. We're actually solving for s in this case, but do we know k? And oh, they give it to us. So our k is equal to 72 newtons per meter. So we just go ahead and plug everything in. So this turns out to be 1/2 0.5, right? 0.5 multiplied by 2.4 squared is equal to 1/2 of 72 multiplied by s squared. So grab your calculators and we're gonna plug this in. 2.4 squared divided by 2 and divided by 72. And then you get s is equal to 0.2. On figure 4.4, sketch the graphs to show the variation of compression x of spring from 0 to maximum compression of 1, the magnitude of the deceleration a of the balls, and 2, the kinetic energy of the balls. Okay. So I know like in a previous problem, we did like this plateau, right? We did this plateau because that as we continue on, we'll eventually like reach infinite like mass kind of. You know, like this goes on forever, depending on the spring, as long as it doesn't break. But essentially, we're going from 0 to maximum. So when this happens, the balls, right? They compress a spring. It compresses a spring until it cannot move anymore, right? So in this case, our force of the springs is pushing out the most. So in this case, the magnitude in this case is actually going to increase. And it's also going to increase linearly. Another way to think of it is like, wait, I'm just going to say like force is equal to MA, right? So force in this case is equal to K over X, Hooke's law, divided by M is equal to A. It's just a linear relation. Linear relation, right? K over M is the constant, multiplied by X is equal to A. So it's like, yeah. So this is like the X variable, this is the Y variable, and this is the slope. And this is linear. Additionally, number 2, the kinetic energy E of K of the balls. So E of K is equal to 1/2 mv squared. And we also know that as we increase compression, right, our E of K goes down, but our E of P goes up, right? So we know that E of P is equal to 1/2 K S squared. In this case, they use X, so you can just use X here. Doesn't really matter. But essentially, as X increases, we start with positive initial energy, right? But this term is actually squared. So it turns out that we go concave down like this. And yeah, this is when you reach maximum compression, right? Our balls are not moving. And yeah, so that's gonna be it. So if you have any questions, just feel free to leave a comment down below. Tomorrow is test day for my class, so make sure to study so you don't fail. Good luck, and don't forget to like.